Alright, this is me reading Programming in Haskell by Graham Hutton. Let's begin. Chapter 1, Introduction. In this chapter, we set the stage for the rest of the book. We start by reviewing the notion of a function, then introduce the concept of functional programming, summarize the main features of Haskell and its historical background, and conclude with 3 small examples that give a taste of Haskell. 1.1 Functions. In Haskell, a function is a mapping that takes one or more arguments and produces a single result, and is defined using an equation that gives a name for the function, a name for each of its arguments, and a body that specifies how the result can be calculated in terms of the arguments. For example, a function double that takes a number x as its argument and produces the result x plus x can be defined by the following equation. Double x is x plus x. When a function is applied to actual arguments, the result is obtained by substituting these arguments into the body of the function in place of the argument names. This process may immediately produce a result that cannot be further simplified, such as a number. More commonly, however, the result will be an expression containing other function applications which must then be processed in the same way to produce the final result. For example, the result of the application of double 3 of the function double to the number 3 can be determined by the following calculation, in which each step is explained by a short comment in curly parentheses. Double 3 equals applying double 3 plus 3 equals applying plus 6. Similarly, the result of the nested application double double 2, in which the function double is applied twice and can be calculated as follows. Double double 2, applying the inner double is 2 plus 2, applying plus double 4, applying double 4 plus 4, applying plus 8. Alternatively, the same result can also be calculated by starting with the outer application of the function rather than the inner. Double double 2, applying the outer double 2 plus double 2, applying the first double, 2 plus 2 plus double 2, applying the first plus, 4 plus double 2, applying double, 4 plus 2 plus 2, applying the second plus, 4 plus 4, applying plus 8. However, this approach requires 2 more steps than our original version, because the expression double 2 is duplicated in the first step and hence simplified twice. In general, the order in which functions are applied in a calculation does not affect the value of the final result, but it may affect the number of steps required and whether the calculation process terminates. These issues are explored in more detail when we consider how expressions are evaluated in Chapter 15. 1.2 Functional Programming. What is functional programming? Opinions differ, and it is difficult to give a precise definition. Generally speaking, however, functional programming can be viewed as a style of programming in which the basic method of computation is the application of functions to arguments. In turn, a functional programming language is one that supports and encourages the functional style. To illustrate these ideas, let us consider the task of computing the sum of 2 integers, whole numbers, between 1 and some larger number n. In many current programming languages, this would normally be achieved by using... In many current programming, it would be achieved by using 2 integer variables whose values can be changed over time by means of the assignment operator equals, with one such variable used to accumulate the total and the other used to count from 1 to n. For example, in Java, the following program computes the required sum using this approach. Int total is 0, for int I count is 1, count is less than or equal to n, count plus plus, total is total plus count. That is, we first initialize an integer variable total to 0 and then enter a loop that ranges an integer variable count from 1 to n, adding the current value of the counter to the total each time round the loop. In the above program, the basic method of computation is changing stored values, in the sense that executing the program results in a sequence of assignments. For example, the case of n equal to 5 gives the following sequence, in which the final value assigned to the variable total is the required sum. Total is 0, count is 1, total is 1. Then it goes all the way up to total is 15. In general, programming languages such as Java, in which the basic method of computation is changing stored values, are called imperative languages, because programs in such languages are constructed from imperative instructions that specify precisely how the computation should proceed. Now, let us consider computing the sum of the numbers between 1 and n using Haskell. This would normally be achieved by using two library functions. One called ... that is used to produce the list of numbers between 1 and n, and the other called sum, that is used to produce the sum of the list. Sum of 1 ... n. In this program, the basic method of computation is applying functions to arguments, in the sense that executing the program results in a sequence of applications. For example, the case of n equal to 5 gives the following sequence, in which the final value is this required sum. In which the final value in the sequence is the required sum. Okay. The sum of, I guess we'll call this range. He didn't really tell us how to pronounce that. The sum of range 1 up to 5, applying range. Sum of the list 1 to 5, applying sum. 1 plus 2 plus 3 plus 5, applying plus 15. Okay. Most imperative languages provide some form of support for programming with functions. So the Haskell program sum of 1 up to n could be translated into such languages. However, many imperative languages do not encourage programming in the functional style. For example, many such languages discourage or prohibit functions from being stored in data structures, such as lists, from constructing intermediate structures, such as the list of numbers in the above example, from taking functions as arguments or producing functions as result, or from being defined in terms of themselves. In contrast, Haskell imposes no such restrictions on how functions can be used, and provides a range of features to make programming with functions both simple and powerful. Okay, so maybe I'll keep my commentary for later, but I feel like he's being a bit deceitful here. 1.3 Features of Haskell. For reference, the main features of Haskell are listed below, along with particular chapters of this book that give further details. Concise programs, chapters 2 and 4. Due to the high-level nature of the functional style, programs written in Haskell are often much more concise than programs written in other languages, as illustrated by the example in the previous section. Moreover, the syntax of Haskell has been designed with concise programs in mind, in particular by having few keywords and by allowing indentation to be used to indicate the structure of programs. Although it is difficult to make an objective comparison, Haskell programs are often between 2 and 10 times shorter than programs written in other languages. Powerful type system, chapters 3 and 8. Most modern programming languages include some form of type system to detect incompatibility errors, such as erroneously attempting to add a number and a character. Haskell has a type system that usually requires little type information from the programmer, but allows a large class of incompatibility errors in programs to be automatically detected prior to their execution, using a sophisticated process called type inference. The Haskell type system is also more powerful than most languages, supporting very general forms of polymorphism and overloading, and providing a wide range of special purpose features concerning types. List comprehensions, chapter 5. One of the most common ways to structure and manipulate data in computing is using lists of values. To this end, Haskell provides lists as a basic concept in the language, together with a simple but powerful comprehension notation that constructs new lists by selecting and filtering elements from one or more existing lists. Using the comprehension notation allows many common functions on lists to be defined in a clear and concise manner, without the need for explicit recursion. Recursive functions, chapter 6. Most programs involve some form of looping. In Haskell, the basic mechanism by which looping is achieved is through recursive functions that are defined in terms of themselves. It can take some time to get used to recursion, particularly for those with experience of programming in other styles. But as we shall see, many computations have a simple and natural definition in terms of recursive functions, especially when pattern matching and guards are used to separate different cases into different equations. Higher order functions, Chapter 7. Haskell is a higher order functional language, which means that functions can freely take functions as arguments and produce functions as results. Using higher order functions allows common programming patterns, such as composing two functions, to be defined as functions within the language itself. More generally, higher order functions can be used to define domain-specific languages within Haskell itself, such as for list processing, interactive processing, and parsing. Effectful functions, Chapter 10 and Chapter 12. Functions in Haskell are pure functions that take all their inputs as arguments and produce all their outputs as results. However, many programs require some form of side effect that would appear to be at odds with purity, such as reading input from the keyboard or writing output to the screen. While the program is running, Haskell provides a uniform framework for programming with effects, without compromising the purity of functions, based upon the use of monads and applicatives. Generic functions, Chapter 12 and 14. Most languages allow functions to be defined that are generic over a range of simple types, such as different forms of numbers. However, the Haskell type system also supports functions that are generic over much richer kinds of structures. For example, the language provides a range of library functions that can be used with any type that is functorial, applicative, monadic, foldable, or traversable, and moreover allows new structures and generic functions over them to be defined. Lazy evaluation, Chapter 15. Haskell programs are executed using a technique called lazy evaluation, which is based upon the idea that no computation should be performed until its result is actually required. As well as avoiding unnecessary computation, lazy evaluation ensures that programs terminate whenever possible, encourages programming in a modular style using intermediate data structures, and even allows modular programming with infinite structures. Equational reasoning, Chapters 16 and 17. Because programs in Haskell are pure functions, simple equational reasoning techniques can be used to execute programs, to transform programs, to prove properties of programs, and even to calculate programs directly from specifications of their intended behavior. Equational reasoning is particularly powerful when combined with the use of induction to reason about functions that are defined using recursion. 1.4 Historical background. Many of the features of Haskell are not new, but were first introduced by other languages. To help place Haskell in context, some of the key historical developments related to the language are briefly summarized below. In the 1930s, Alonzo Church developed the lambda calculus, a simple but powerful mathematical theory of functions. In the 1950s, John McCarthy developed Lisp, list processor, generally regarded as being the first functional programming language. Lisp had some influences from the lambda calculus, but still retained the concept of variable assignment as a central feature of the language. In the 1960s, maybe I shouldn't read all this. Okay. It is worthy to note that three of the above individuals, McCarthy, Backus, and Milner, have each received a ACM Turing Award, which is generally regarded as being the computing equivalent of a Nobel Prize. 1.5 A taste of Haskell. We conclude this chapter with three small examples that give a taste of programming in Haskell. The examples involve processing lists of values of different types and illustrate different features of the language. Summing numbers. Recall the function sum used earlier in this chapter, which produces the sum of a list of numbers. In Haskell, sum can be defined using two equations. Sum of the empty list equals 0, sum of n and n's is equal to n plus the sum of n's. The first equation states that the sum of the empty list is 0, while the second states that the sum of any non-empty list comprising of a first number n and a remaining list of numbers n's is given by adding n and the sum of n's. For example, the result of sum applied to the list 1, 2, 3 can be calculated as follows. Sum of 1, 2, 3, 1, 2, 3, applying sum, 1 plus sum of 2 and 3, applying sum, 1 plus 2 plus sum of 3, applying sum, 1 plus 2 plus 3 plus 0, applying plus 6. Note that even though the function sum is defined in terms of itself and is hence recursive, it does not loop forever. In particular, each application of sum reduces the length of the argument list by 1 until the list eventually becomes empty, at which point the recursion stops and the additions are performed. Returning 0 as the sum of the empty list is appropriate because 0 is the identity for addition. That is, 0 plus x is x and x plus 0 is x for any number x. In Haskell, every function has a type that specifies the nature of its arguments and results, which is automatically inferred from the definition of the function. For example, the function sum defined above has the following type. Num a, then list of a's to a. This type states that for any type a of numbers, sum is a function that maps a list of such numbers to a single such number. Haskell supports many different types of numbers, including integers such as 123, and floating point numbers such as pi. Hence, for example, sum could be applied to a list of integers, as the calculation above, or to a list of floating point numbers. Types provide useful information about the nature of functions, but more importantly, their use allows many errors in programs to be automatically detected prior to executing the programs themselves. In particular, for every occurrence of function application in a program, a check is made that the type of the actual arguments is compatible with the type of the function itself. For example, attempting to apply the function sum to a list of characters would be reported as an error because characters are not a type of numbers. Sorting values. Now let us consider a more sophisticated function concerning lists, which illustrate a number of other aspects of Haskell. Suppose that we define a function called qsort by the following two equations. Qsort of the empty list qsort of x and x's, qsort of smaller plus the singleton list x plus qsort of larger, where smaller is, I think that's a list comprehension then. I don't know how to read that, but I think so. Smaller is the list of numbers smaller than x, and larger is the list of x is larger than x. The list of x is larger than x. In this definition, okay, it's going to explain it. In this definition, plus is an operator that appends two lists together. For example, list 1, 2, 3 plus list 4, 5 is 1, 2, 3, 4, 5. In turn, where is a keyword that introduces local definitions. In this case, a list smaller comprising all elements A from the list x's that are less than or equal to x, together with a list larger comprising all elements B from x's that are greater than x. For example, if x is 3 and x is 4, 1, 4, 2, then smaller is 1, 2, and larger is 5, 4. What does qsort actually do? First of all, we note that it has no effect on lists with a single element, in the sense that qsort of a list which only contains x is x for any x. It is easy to verify this property using a simple calculation. Qsort of the list containing x, applying qsort. Applying qsort, the empty list plus x plus the empty list, applying plus the empty list, the list containing x. In turn, we now work through the application of qsort to an example list. using the above property to simplify the calculation. Okay, I think we get it. He made quicksort. In summary, qsort has sorted the example list into numerical order. More generally, this function produces a sorted version of any list of numbers. The first equation for qsort states that the empty list is already sorted, while the second states that any non-empty list can be sorted by inserting the first number between the two lists that result from sorting the remaining numbers that are smaller and larger than this number. This method of sorting is called quicksort and is one of the best such methods known. So I wonder, oh yeah, so equals is in the smaller. The above implementation of quicksort is an excellent example of the power of Haskell, being both clear and concise. Moreover, the function qsort is also more general than might be expected, being applicable not just with numbers, but with any type of ordered values. More precisely, the type qsort is of the type ordable or something? Ordinal? Ordable. Goes from a list of A's to a list of A's. States that for any type of ordered values, qsort is a function that maps between lists of such values. Haskell supports many different types of ordered values, including numbers, single characters such as A, and strings of characters such as A, B, C, D, E. Hence, for example, the function qsort could also be used to sort a list of characters or a list of strings. Okay. I wonder if that works with just the values of Unicode or sequencing actions. Our third and final example further emphasizes the level of precision and generality that can be achieved in Haskell. Consider a function called sequen that takes a list of input-output actions, such as reading or writing a single character, performs each of these actions in sequence, and returns a list of resulting values. In Haskell, this function can be defined as follows. Wait, what? I didn't really... Consider function performs each of these actions in sequence. Sequence of the empty list, return the empty list. Sequence of acts, do x, x's, sequence acts, return x and x's. Oh, so they're immediately introducing do notation. That's interesting. These two equations state that if the list of actions is empty, return the empty list of results. Otherwise, we perform the first action in the list, then perform the remaining actions, and finally return the list of results that were produced. For example, the expression sequence get car, care, I don't know, reads 3 characters from the keyboard using the action get care that reads a single character and returns a list containing the 3 characters. Okay. So it also returns a value in the end. Okay. The interesting aspect of the function sequence is its type. One possible type that can be inferred from the above function is the following. Sequence takes a list of IO actions, and returns IO of a list of A's. This type states that sequence maps a list of IO input-output actions that produce results of some type A to a single IO action that produces a list of such results, which captures the high-level behavior of sequence in a clear and concise manner. More importantly, however, the type also makes explicit that the function sequence involves the side effect of performing input-output actions. Using types in this manner to keep a clear distinction between functions that are pure and those that involve side effects is a central aspect of Haskell, and brings important benefits in terms of both programming and reasoning. In fact, the function sequence is more general than it may initially appear. In particular, the manner in which the function is defined is not specific to the case of input-output actions, but is equally valid for other forms of effects too. For example, it can also be used to sequence actions that may change stored values, fail to succeed, write to a log file, and so on. This flexibility is captured in Haskell by means of the following more general type. Sequence takes a monad. Sequence M is of a monadic type. We take a list of M monads and return a monad of a list or something. That is, for any monadic type M, of which IO is just one example, sequence maps a list of actions of type M into a single action that returns a list of values of type A. Being able to define generic functions such as sequence that can be used with different kinds of effects is a key feature of Haskell. 1.6 Chapter Remarks. The Haskell report, blah blah blah. Okay. Exercises. Give another possible calculation for the result of double double 2. Okay, so let's go back. Maybe I should have done a search. Okay. Okay, so he first did applying the inner double. So I think this is just applicative order, and then he does applying the outer, applying the first double. I mean, we could just like first apply this second double here, I think. So let's make like oops. Nope. What is it doing? Okay, so maybe we can just copy that. No. Okay, so applying outer double. Applying the first double. So here we're just gonna do second double, and this becomes double 2. Applying the second plus double 2 plus 4. Applying the double. Maybe we'll just write applying double 2 plus 2 plus 4. Applying plus 8. Oof, that was kind of painful. Okay. Okay. Show that sum of the list of x is x for any number x. Show that. So he's asking me to like write a proof. What is he asking me here? Maybe we'll like. I don't know if this is gonna work. haven't used Emacs in a while. So. Exercise 2. So let's go back to the definition of sum. Okay. Apply recursive definition of sum. Then sum of x is equal to x plus the sum of the empty list. Apply definition of sum of empty list. Sum of x is equal to x plus 0. Apply definition of, maybe we should like maybe we should write it like this. Like this. I'm not sure if this is what he meant, but oops. Define, okay, here we go, some programming. Okay, so here I just have Haskell, and then I can load it down here, and you can see what I did before. So I think I'll just delete this and say, define a function product that produces the product of a list of numbers, and show using your definition that product of 2, 3, 4 is 24. Okay, so product of the empty list is 1 then. It's kind of strange, but if we, yeah, I think that's going to be it. Product of x and x's is x times product of x's. Let's see if that works. Nope, that doesn't work. Okay, so the function is already defined. Prod, and let's see if it works. Prod of 2, 3, 4. Boom. Yeah, that's correct. So I wonder. Okay. How should the definition of the function qsort be modified so that it produces a reverse sorted version of the list? Let's take a look. So I think this is an image. Okay, so I have to type it over. Oh, wait. Let's see. Qsort. Maybe we'll call it, I don't know. Let's call it reverse qsort. Maybe I'll just first just copy it. Let's see if this compiles. Nope. Variable not in sort. Oh, okay. Reverse qsort. Okay. So now, how do we reverse this? So this should be then larger, smaller. Is it that easy? Maybe I can just do up arrow. I don't really know how this interpreter works. This REPL. Is that right? 9, 5, 4, 3. Yeah. Okay, that was easier than expected. Exercise 5. What should be the effect of replacing smaller than or equal by smaller in the original definition of Q-sort? Hint, consider the example Q-sort 22311. Okay, let's think about it before we actually do it, right? Maybe I'll smaller, larger. So let's say we replace this by smaller than. I think it's just gonna remove duplicates. Because at some point every number in the list is x. And then the smaller ones, the ones that are equal are going to get filtered out. So let's see what happens. 2, 2, 3, 1, 1. Yep. Are we going to look at the solutions? Nope. Chapter 2. First steps. In this chapter, we take our first proper steps with Haskell. Haskell? I've been saying it two ways. Haskell or Haskell, I don't really know. We start by introducing the GHC system and the standard prelude. Then explain the notation for function application, develop our first Haskell script, and conclude by discussing a number of syntactic conventions concerning scripts. 2.1 Glasgow Haskell Compiler. As we saw in the previous chapter, small Haskell programs can be executed by hand. In practice, however, we usually require a system that can execute programs automatically. In this book, we use the Glasgow Haskell Compiler, a state-of-the-art open-source implementation of Haskell. And might I add, the only implementation of Haskell. There's Hugs, I think, but it's not maintained anymore. Oops. Well, anyways, what is that? Leaks. Ooh. Let's not get distracted. The system has two main components, a batch compiler called GHC and an interactive interpreter called GHCI. We will primarily use the interpreter in this book as its interactive nature makes it well suited for teaching and prototyping purposes, and its performance is sufficient for most of our applications. However, if greater performance or a standalone executable version of Haskell program is required, the compiler itself can be used. For example, we will use the compiler in extended programming examples in chapters 9 and 11. Installing and starting, I've already done that. How did he expect us to do the previous exercise without a Haskell installation? Following normal mathematical convention. He's explaining some Haskell stuff. Standard prelude. Haskell comes with a large number of built-in functions, which are defined in a library file called the standard prelude. In addition to familiar numeric functions such as plus and asterisk, multiplication, the prelude also provides a range of useful functions that can operate on lists. In Haskell, the elements of A lists are enclosed in square parentheses and are separated by commas, as in 1, 2, 3, 4, 5. Some of the most commonly used library functions on lists are illustrated below. Head, tail. So he says here, plus is defined in the prelude. I would think that plus is like built in. Oh, I think I have to do it like this maybe. That's interesting. So head takes the first, tail takes the last. The car and the cutter. Select the nth element of list counting from 0. Select the first n elements of a list, take. Remove the first n elements of a list, drop. Calculate the length of a list. Calculate the sum of the list. Calculate the product. Append to lists. Reverse a list. As a useful reference guide, Appendix B presents some of the most commonly used functions from the standard prelude. 2.4 Function application. In mathematics, the application of a function to its parameters is usually denoted with enclosing arguments in parentheses, while the multiplication of two values is often denoted silently. By writing the two values next to one another, for example, in mathematics, the expression f of a and b plus c d means the function f of two arguments a and b, and add the result of the product of c and d, reflecting its central status in the language. Function application in Haskell is denoted silently using spacing, while the multiplication of two values is denoted explicitly using the asterisk operator. For example, the expression above would be written in Haskell as follows: f of a b plus c times d. Moreover, function application has higher priority than all other operators in the language. For example, f of a plus b means f of a plus b, rather than f of a plus b. So plus is not a function? What do you mean? The following table gives a few further examples to illustrate the differences between function application in mathematics and in Haskell. I understand what he's saying, but note that parentheses are still required in Haskell expressions. In the Haskell expression f of g of x above, because f of g of x on its own would be interpreted as the application of the function f to two arguments g and x, whereas the intention is that f is applied to one argument, namely the result of applying the function to an argument x. A similar remark holds for the expression f of x of g of y. But I have can you do like, so now we can do like f of g of 3, but you can also do it like this, right? Oh no. How does that work? Haskell scripts. As well as the functions provided in the standard prelude, it is also possible to define new functions. Really? Surprising, we haven't done that before. New functions are defined in a script, a text file comprising a sequence of definitions. By convention, Haskell scripts usually have an sh suffix on their file name to differentiate them from other kinds of files. This is not mandatory, but is useful for identification purposes. My first script. When developing a Haskell script, it is useful to keep two windows open, one running an editor for the script and the other running GH. Yeah, as an example, blah, blah, blah. Yeah, we're already doing that. For reference, blah, 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 blah. Naming requirements. When defining a new function, the names of the function and its arguments must begin with a lowercase letter, but can be followed by 0 or more letters, both lower and uppercase, digits, underscores, and forward single quotes. For example, the following are all valid names. The following list of keywords have a special meaning in the language and cannot be used as the names of functions of their arguments. By convention, okay. By convention, list arguments in Haskell usually have the suffix s on their name to indicate that they may contain multiple values. For example, a list of numbers might be named n's, a list of arbitrary values might be named x's, and a list of lists of characters might be named CSS, cascading style sheets. Well, that's really confusing to me. A list of lists of characters might be named CSS. A list of C's. A list of C's. Okay. The layout rule. Within a script, each definition at the same level must begin in precisely the same column. This layout rule makes it possible to determine the grouping of definitions from their indentation. For example, in the script, A is B plus C. Okay, yeah, I think this doesn't work in the ebook. It is clear from the indentation that B and C are local definitions for use within the body of A. If desired, such grouping can be made explicit by enclosing a sequence of definitions in curly parentheses and separating each definition with a semicolon. For example, the above script could also be written as that. Or even be combined into a single line. In general, however, it is usually preferable to rely on the layout rule to determine the grouping of definitions, rather than using explicit syntax. Yeah. Now, one thing I want to say is why the frick are the variables defined after the expression? That's so unreadable. Why isn't it like let B equal 1, C equal 2 in A is B plus C? That would be way more logical in my opinion. Although I think let is also a thing in so that also exists. But why is he writing it backwards here? I don't know. Tabs. Tab characters can cause problems in scripts because layout is significant, but different text editors interpret tabs in different ways. For this reason, it is recommended to avoid using tabs when indenting definitions, and the GHC system issues a warning message if they are used. Okay, so I think Emacs just converts them to spaces. If you do wish to use tabs in your scripts, it is best to configure your editor to automatically convert them to spaces. Haskell assumes that tab stops are 8 characters wide. Comments. In addition to new definitions, scripts can also contain comments that will be ignored by the compiler. Haskell supports 2 types of comments called ordinary and nested. Ordinary comments begin with the symbol .. and extend to the end of the current line, as in the following examples. Nested comments begin and end with the symbols curly dash and dash curly. Wow, that's weird. Oh. Now what if I do this? Okay. Oh. And what if I do this? Okay. Factorial. We already read that. Oh, very clear example where he writes code in a comment. 2.6 chapter remarks. Okay. Remember, work to the examples from this chapter using JHCI, parenthesize the following numeric expressions. So are we gonna do, I feel like exercise 1 is just copying a bunch of shit, so I'm not gonna do that. Exercise 2, parenthesize the following numeric expressions. Parenthesize? What? Like, not in Haskell? What do you mean, bro? So he means like do this. Okay, yeah, this exercise is done. Exercise 3. The script below contains 3 syntactic errors. Correct these errors and then check that your script works properly using the GHCI. Okay, maybe I'll copy that. Oh. How does he write that again? So oh my god. Okay, so I think I should look into setting this up better in oh, maybe this should be here or something. Okay. Lexical error. What? You didn't even explain these backward things. What even is that? Is that a quote? No. What? Syntax error. I did not mean to use template Haskell. Not in scope. Data constructor N. Oh yeah, it's a capital letter. What? This exercise sucks. Like the dude is like introducing converting functions to infix functions in an exercise, and he used wrong syntax. What the hell? This book is not as good as I thought it was going to be. And the whole exercise was convert this n into a lowercase letter? What the hell? Okay. Exercise 4. The library function last selects the last element of a non-empty list. For example, last of 1, 2, 3, 4, 5 is 5. Show how the function last could be defined in terms of the other library functions introduced in this chapter. Can you think of another possible definition? Okay. So I think maybe we can do like, okay, so we have to give it a new name. Last 2 of ends is we could maybe do take 1 of reverse ends. No. Here, take reverse. Maybe it has to do with maybe this. I don't really know. No, there's like a thing to say first do that and then do that, so you have to write less parentheses. Last. Oh, that's really confusing. Last 2, because it last new. No, last different oh, does it have, oh yeah, it's autocomplete. Boom. Or we could do, what? First I was thinking of doing oh yeah, we can write this as head. That's okay. Let's try if we, no, that doesn't work. You cannot. Oh, maybe I can just do this. Boom. We could also maybe do I was thinking maybe we can do like drop everything but the last one, and then we have a singleton list, and then we take the head. It's kind of silly, but head of drop, I think. Drop length of ends, and then we do that -1 of ends. Let's see if that works. Last. Boom, that also works. Okay. Chapter 5. The library function init removes the last element from a non-empty list. For example, init of 1, 2, 3. Show how init could similarly be defined in two different ways. Init different ends. So it removes the last one. So it's the reverse of tail of reverse ends. Boom. Or how else? Oh yeah, with drop. I mean, we can just replace tail with drop 1. That's kind of silly. I guess we solved the exercise. Okay. Chapter 3. Maybe I'll stop it here because we've done 1 hour. See you later.